Hi, I'm Dr. Courtney with Carmel Academy. Thanks for joining us in this science laboratory series where our goal is to teach you how to do science like a boss. And how do I know that you can do science like a boss? It's simple, because God said so. In Genesis 1, God said to be fruitful and multiply, fill the earth and subdue it, to rule over the fish of the seas and the birds of the air and everything that moves along the ground. So God created man to exercise rulership and authority over creation. And part of that rulership and authority comes through the exercise and the discipline of science. So we know we can do science like a boss. The hypothesis for today's experiment on the relationship of mass to volume is that mass is proportional to volume. So this is our hypothesis. And what makes this hypothesis worthy of being tested scientifically in an experiment? Well, it's very simple. God could have created the universe with different physical properties. God could have made mass go as the square of volume. God could have made the mass not have any recognizable mathematical relationship to volume. God could have created a universe where mass and volume didn't exist. So it's an interesting question to ask, and it can be tested experimentally reasonably simply. And our experimental design is simply to use a laboratory balance and a graduated cylinder to measure the volume and then the mass of several test liquids, and then we can analyze that data after we record it carefully in our lab notebook. We can analyze that data to test the hypothesis that mass is proportional to volume. And some things about the experimental design, most of the times when you're doing things in science, you want to try and control for external factors. You want to recognize there's always some fine print on a hypothesis, and some of the fine print here is that the mass of uniform substances is proportional to the volume of the uniform substance. And so there's also some fine print about well-controlled conditions and careful experiments. And so, alright, we've chosen to do our experiment in three relatively common liquids: distilled water, acetone, and isopropyl alcohol. But there's no overwhelmingly strong reasons for these three choices. The hypothesis is quite general. We don't want to test it in only one substance because it may be true in that one substance and not true in any others. So we choose several substances, and liquids are particularly convenient because it's easy to measure their volume in the graduated cylinder. But you know, if you don't like our liquids or you've got other stuff on hand, you could use corn syrup, vegetable oil, honey. There's lots of interesting choices of experimental liquids for this experiment. Okay, so we prepare our lab notebook with a table, and of course zero volume is going to have zero mass, and we're measuring the volume in milliliters and the mass in grams. And then we're going to go up by steps of 10 milliliters, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And we're going to measure the mass of these different quantities of water, volumes of water. So we take a little care here. We prepare by pouring our distilled water into a beaker, and a beaker is simply a convenient container for holding, start off with a little more than 100 milliliters, because we're going to gradually transfer the water from the beaker to the graduated cylinder in order to measure the mass in different steps in the sequence. But the first thing we want to do is we want to measure the mass of the graduated cylinder without the water. So measuring the mass of the graduated cylinder without the water, and we just see GC stands for graduated cylinder, and that's 37.3 grams is the units. And this laboratory balance has the nice feature that we can press this button here and zero it out. So it kind of tells it that you're using the standard piece of laboratory equipment, the graduated cylinder, to measure the mass of something in, so it subtracts that out automatically. So you can see when we take it off, it reads negative 37.5 grams. So now we just need to prepare to carefully add 10 milliliters at a time of water to the graduated cylinder. And you might not be able to see me doing it, some of it's off camera, but I'm using a smaller graduated cylinder, and we've got a medicine dropper or an eyedropper there to carefully add 10 milliliters at a time. And you want to be careful to read the graduated cylinder accurately and with care. So there's what's called a meniscus. You don't measure the top of the curve, but there's a little bit of a bow down at the bottom. So let's get down there with the camera, see how well we can see this in the graduated cylinder. So we've got the water in there, and now we've got a little what's called parallax, because the camera is looking at the water in the graduated cylinder from an upward level. So if you were to say how much water is in the graduated cylinder right now, you'd probably conclude it's between 10 and 12 milliliters, but that's incorrect because we're looking at a downward angle with the camera. We want to take care to look from a level position. So when we take due care to look at it from a level position, we can see that there's, at least as close as the eye can line it up, 10 milliliters of water in the graduated cylinder. So the mass of the 10 milliliters of water in the graduated cylinder is 9.7 grams. And then we just repeat that process, add 10 more milliliters to make 20 milliliters, measure its mass, and so on in a careful, repeatable manner. And the smaller graduated cylinder is particularly convenient for adding additional water in increments of 10 milliliters, but we don't completely trust just the fact that we added it from the smaller graduated cylinder. We go ahead and get down there eye level and check that the meniscus does line up with the 20 milliliter mark, and then we write down the next mass. This is the mass of 20 milliliters of water, 19.5 grams. Now we'd be prepared to top it off if the meniscus didn't line up just right. That's what the medicine dropper here is for. We'd come up to the top and we'd add a few more drops. But it's important to take the graduated cylinder off of the electronic balance when adding water. Well, why is that? Because in science there's a phenomenon called bias. When the experimenter has in mind an expected outcome, maybe in line with his hypothesis, it might be that the experimenter adds a little more or a little less water if he happens to be looking at the mass because he's got some expectation of what the mass should be. So to prevent bias, we make sure that we remove the graduated cylinder from the balance when we're adding water, and then we convince ourselves to the best of our ability that we've added the desired amount of water, and only then do we move the graduated cylinder to the balance to measure the mass. So first we measure the volume carefully in the graduated cylinder using the meniscus and so on, and then we measure the mass. $59.6 70 milliliters has a mass of 69.8 grams, and so it's 89.8 grams, 99.8 grams. Data notebook in view. That concludes what I ordinarily like to call the experimental portion of a lab, when one actually collects the data, or at least we've got the first third of it done, right? We've concluded the experimental portion for the material of distilled water. We still have to go isopropyl alcohol and acetone. Okay, well, here is the spreadsheet that we have set up, and spreadsheets are freely available. If you don't happen to have Microsoft Excel on your computer, you can download LibreOffice or OpenOffice for free. They also have a spreadsheet in Google Docs that can perform this analysis also. So we make sure we put in the what we're doing, mass versus volume. We put in the specific laboratory balance that we're using, which is the U.S. benchtop 2,000 gram balance, the 100 milliliter plastic graduated cylinder, and let's put in the mass of the graduated cylinder that we wrote down, 37.3 grams. The temperature in the room, and this is, we write this down because we happen to have a thermometer in our laboratory, and most homes have a thermometer, and most classrooms have a thermometer, and usually the temperature is somewhere between 70 and 75 degrees Fahrenheit, and that's just in case some question arises with regard to the density or the relationship with mass over mass to volume. Was the temperature changing or something of those lines? We have it written down. And now we have our sample number in this column, and we're going to go ahead and we entered in our volumes in this column, and then we want to enter in this column the masses that we measured, 9.7 grams for 10, and then 19.5. We want to need to take some care in data entry, 29.3, 39.1, 49.7, 59.6, 69.8, 79.6, 89.8, and 99.8. So those were the 10 masses that we measured, so we just enter them into a table in the spreadsheet. And this is where the fun starts. We've got a special spreadsheet command that we're going to enter, and what this spreadsheet command does is it does a least square fit to a straight line for the data, and we can also tell it that don't just do a least square fit to a straight line, because you might recall that the equation of a line is y equals mx plus b, but we can force it to make the b, the y-intercept, equal to 0 to force the line to go through the origin, because that represents the mathematical test of the hypothesis of a proportionality, because that was the hypothesis rather than a linear relationship. Because a linear relationship could have any vertical intercept. So the command is equal, somehow I ended minus, equals linest, L-I-N-E-S-T, and then open paren, and then we want the elements that contain the masses, so that is C7 colon C16, and then we want the elements that contain the volume, so that's equal B7 colon B16. And then there's a couple other entry fields here, and one is the linear type, and the linear type 0 says make the vertical intercept 0, and then the stats, the last entry, tells us that we do want the statistics that it's going to output. And then there's another special thing that one has to do that's a little different from a lot of spreadsheet calls, is before one hits return, one hits shift, control, and return, because it returns a whole array of different values, and those different values have specific meanings, and we can talk about those specific meanings. So the spreadsheet call conducted a least square fit, and the slope it returned is 0.99499. And so that's the proportionality constant in the hypothetical proportional relationship. And this column here, that would be the y-intercept, that value that's 0, but we forced it to be 0 in the way that we gave the command. Now the uncertainty in the slope is 0.00186. And the r squared, if you're familiar with least square fits, you've ever seen them before, the r squared value is a measure of goodness of fit, and 0 means you don't have any goodness of fit. You don't really have a mathematical relationship. And r squareds vary from 0 to 1, and the closer the r squared value is to 1, then the better the mathematical fit. And so we can see the r squared is 0.9997. So that's very close to 1. So we do have a high level of confidence in our goodness of fit. Now let's go ahead and let's analyze the data in a more traditional way, perhaps, by graphing it. And so we have a graphing program called GraphEXE, which can be downloaded from an internet site. It's free as well, and we can insert a point series. So we just copy our data which we took, which was the data for the mass versus volume, and let's go ahead, we copied it, and so let's graph it. And then if you zoom and you do fit, it'll adjust the x and y axes to display the data in a sensible way. And then one can also label the axes carefully. And so the x-axis, or the horizontal axis here, we don't just need to call x. The horizontal axis was our input variable, which was volume, because the volume was the thing we were controlling in the experiment, and the units of volume were milliliters. And we can also control the range of display there, so let's make it 1 to 110, and let's go ahead, well, let's not auto tick, let's make the tick units 10. And that's one of the things I really like about this GraphEXE program, is it's easy to adjust all the display parameters and end up with something that's really going to look good in a lab report. So now the vertical axis isn't y, but it's the mass. The units are grams, and we can also adjust the display from maybe 0 to 110. And so now we have a pretty good looking graph here. We've got our raw data, and we can also do a similar analysis here where we insert a trend line. We tell it that we want a linear trend line, and we force the y-intercept to be 0, and so it doesn't display as many significant figures in the slope or the value of r squared, but it gives you the same idea. So this is a graphical view that also looks like it supports our hypothesis. Well, if you've ever read the instructions on a bottle of shampoo, it explains how to use shampoo, and then it says lather, rinse, repeat. And this is the stage of the experiment where we're at the lather, rinse, repeat stage. I don't think you're going to learn much by watching me repeat the experiment in acetone and isopropanol, but you and students will learn a lot by actually going through and repeating the experiment with 3 different substances, because 3 different substances is going to give a much higher level of confidence that this hypothetical proportionality might be a more universal property of uniform materials rather than being something that only applies to water. Thanks for joining us today at Carmel Academy. I'm Dr. Courtney.